In this video and in the next video also, we are going to have prerequisites for the main objective of the section, namely any two splitting fields of the same polynomial are isomorphic. So this result, which is given as lemma 5.3.3 in Hurston, states that if tau from f to f prime is one-to-one onto homomorphism, then tau star, which is from collection of all polynomials over f to this collection of all polynomials over f prime. So f and f prime are two fields. There is no connection between this prime what we use here and in the derivatives that the derivative of f of x is f dash of x. There is no connection between this notation and the derivative what we use in differentiation. So this tau prime from fx to f prime is one-to-one onto homomorphism with the property that it takes the element of f to the element of f prime for every, that is, base field. It is polynomial f of x when we consider small f of x. It's a polynomial over f, and there f dash of t we will refer it as, so that will be a polynomial over f dash. That collection is capital F prime t, and collection of all polynomials which we denote as f of x over f is in this collection. So what is given to me is only this: tau from f to f prime is one-to-one onto homomorphism. If that is the case, then we have all this. We can have from fx to f prime of t a mapping which is one-to-one onto an homomorphism. Now the entire proof of uniqueness of splitting fields lies here. This is to be noted. This is the catalyst, what we call in chemical reactions. So like that, here you have this statement: if tau from f to f prime is one-to-one onto homomorphism. This is the main thing. And at the beginning, if you have noticed, how is that you can assume that there are two fields f and f prime, so that we can have tau to be one-to-one and onto homomorphism, and that answer will be given at the end of nearly at the end of the proof of any two splitting fields of the same polynomial are isomorphic. There you will reveal, you will see the whether such a thing exists, because at the beginning we assume it. What is a guarantee? So that will be guaranteed at the end. You wait and see that. Very nice. See, actually, the way in which the proof is given that two splitting fields, when we have for a given polynomial, that they are isomorphic, the way in which it is taken is very beautiful, and that must be enjoyed, not just for the examination sake that you need to go through this. Right, now to prove this lemma, we'll consider tau from f to f prime to be the given one-to-one onto homomorphism, which takes alpha to alpha prime. This is our assumption. Now we'll define tau star from fx to f dash of t as it takes f of x to this, meaning if I consider any polynomial in terms of x, it will be converted in terms of t. So that is the meaning, and the scalars in f are nothing but the scalars in f prime under this mapping. Under this rule rather, because we have only defined that it is a rule. Now it have to be proved as mapping, so for which well definedness is to be checked. So we consider two elements in the domain to be equal, and we have to establish the corresponding images are equal in order to have tau star, which is defined as a rule at the beginning, to be a mapping. So we consider f of x to be equal to g of x. You take f of x as this and g of x as this. Then we know that the equality of polynomials means we have to equate the corresponding um, um, coefficients of like powers. So you have alpha n to be equal to beta n and so on, alpha naught equal to beta naught. So alpha, so because tau is a mapping, we can have the image of this to be mapping means well definedness is there. So elements in the domain are equal means the images must be equal. So under any mapping, so you have this, but this is nothing but alpha I prime and this is nothing but beta I prime. So when you consider your f dash of t, that is the image of f of x and tau star which is f dash of t, so that becomes as this, but you have proved already that alpha n prime to be equal to beta n prime, and this is nothing but the g dash of e, which is the image of g of x and a tau star. So this is g dash of t, which is nothing but the image of g of x and a tau star. So tau star is well defined. Now to prove that it is one to one, we are going to prove that it is one to one. So we can just retrace the steps and we can say that it is one to one. Otherwise, we will consider the images to be equal. So we will have this to be beta n, the one with degree n with scalars alphas, and another, g of x, the same degree with betas as coefficients. So your f of x, the image of f of x and the tau star will be this. And because you have taken f dash of t to be equal to g dash of t, that is our assumption. Images equal should imply pre-images equal for one to one. So this becomes beta n prime t power n and so on up to beta naught prime, which is the image of g of x and a tau star. Now we have taken both of them to be of the same degree. So equating the coefficients of like powers. So automatically you will get this. Um, but this one alpha I prime, beta I prime, it is nothing but the image of alpha I under tau, and this is image of beta I under tau. Right. Now, if we consider tau, we have already said that it is one to one. So the images equal means pre-images should be equal. So this is what we get. Because we have taken both of them to be of the same degree, there is no need to discuss all this. So we have the pre-images to be equal, for which you consider f of x. So this is what you have, and that is nothing but because alpha is equal to betas you have established. So that in turn gives this. So our assumption that f dash of t equal to g dash of t, which means f of x, image of f of x, and the tau star equal to image of g of x and the tau star, now implies that f of x equals g of x, which means the pre-images are equal and therefore tau star is one to one. So for well defined, from when you go from fx to f dash of t under tau star, if you consider two elements here equal, implies the corresponding images equal. So that is for, this one is for well definedness. If you come from there to here, it is for one to one. So we have established one to one. Next is the surjective onto part. Now because tau is onto, for every scalar in f prime, you will have a scalar in f such that this one is true. But our job is to show that tau star is onto. So you consider any arbitrary element in the codomain. What is our codomain? F dash of t. Your tau star is a mapping from fx to f dash of t. So when you want to show that this tau star is onto, where from you have to start? Only from the codomain. So there you consider an element, say f dash of t, and let it be this polynomial. But you know that this is the image of this under tau star. How? Because for this one you have already said that alpha n exists. For this you have said that alpha n minus 1 exists. For this you have said that alpha 1 exists, and for this alpha not exists. So we can very well write, so that only because of tau is on to we are able to write this. So you have this to be tau star, I mean image of this and a tau star. If you take that as say f of x, then because this is taken as f dash of t, f of x, so the image of f of x and a tau star. So for every element here you are able to find one pre-image, namely f of x in the domain. So your tau star is onto, and then we have to prove that it is a homomorphism. Homomorphism, both of them being basically rings, we will establish ring homomorphism. Homomorphism means here there are two operations based on the structure only. The conditions you have for homomorphism that is known to you. Here the operations are addition and multiplication of polynomials. So two conditions. So these two conditions are to be checked under addition and under multiplication. It separates f of x plus g of x. Tau star is this. So if for the first one we shall consider f of x as this, g of x. There is no need to have both of them to be of the same degree. They can be different. So we will consider this whenever you have two numbers. By law of trichotomy, you will have to assume one of the two, m greater than n or m less than n or m equals n. So m equals n will come automatically once you prove for either m greater than n or n greater than m. So here we consider the left hand side of this f of x plus g of x. So when we add these two, we have alpha naught plus beta naught and so on up to n. We have the same, and then from n plus 1 to m only betas will exist. So that is why you have this step, and this is tau star, and this is nothing but by the definition. See, whenever you have f of x, what tau star will do, it will take it to f dash of t. So you have got this polynomial. So wherever you have x, it will be taken as a t. So you have alpha naught plus beta naught, the image of this under this one. Actually prime we could have written, but to be on the safe side we have just written tau itself. So this x is taken as t, x power n taken as t power n. But how about all this? So that under tau, that under tau, that under tau only we have kept on writing. So because tau is a homomorphism, you can write like this. And here also tau is a homomorphism, you have like this. Tau is a homomorphism. So all these steps is because tau is a homomorphism. So you have this, and how it is defined we know. Alpha naught prime, beta naught prime, alpha 1 prime, beta 1 prime. Our tau star replaces x by t, that we have written. And whenever you have, say simply when you have a naught plus a1x, very simple polynomial. When you consider this, how this one is taken, just a naught tau plus a1 tau t. This is how it is defined, which we have simply written a naught prime plus a1 prime t. That is denoted as f dash of t. But actual procedure, what has taken place here is only this. So we that is what is explained here. So you have then you can split and write like this. So this in turn gives f of x, the image of f of x under tau star plus image of g of x under tau star. So that is your RHS. Now for the polynomial product, you have this again same procedure. You multiply them. When you multiply, you get like this, and again the same thing. In the place of x, you will have t, and this one the image of this and a tau. Tau being a homomorphism, you have this step, and from which you can easily see that this is nothing but the product. You can compute this separately and show that that is same as this. So you have this to be the image of f of x under tau star, and this is image of g of x under tau star. So we have established this tau star, which is a mapping from this to this, is 1 to 1 on to, and homomorphism. We defined it and showed that it is well defined also. Right. Next, we have this result, which states that the behavior of polynomials in fx is same as the behavior of polynomials in f dash t. So if the polynomial over here, you have set of polynomials which are irreducible, they will be corresponding images will be irreducible in the codomain. And whenever you have polynomial in the codomain to be irreducible, you will have its pre-image also to be irreducible. There is a connection between the polynomials behavior in the domain and codomain. Irreducible implies irreducible of the same polynomial, the image of that under tau star, under tau star. So if f of x means f dash of t. If this is irreducible, image irreducible. If image is irreducible, pre-image is irreducible in both ways. So that is what we are going to establish in this proposition. Which is we can take it as some result. If f of x is irreducible in fx, then f dash of t is irreducible, and vice versa. Right. Now let us take f of x to be irreducible in fx. We shall name that as statement P. What we claim is f dash of t, f prime of t is irreducible in f prime of t. Suppose f prime of t is reducible, which means you can write f prime of t as product of two polynomials like this. But this is nothing but the image of f of x under tau star, and this is, just now we proved tau star is a homomorphism, so we can write like this. But tau star is 1 to 1, so this would imply that f of x equals r of x into s of x. Tau star is a one-to-one mapping, you have this. But this contradicts our statement P, because it says that f of x is irreducible. You have factorized that, which means it becomes reducible. That's a contradiction to statement P. So your f prime of t is irreducible. Now conversely, if you take f prime of t to be irreducible, then f of x is also irreducible. So we suppose, again the same procedure, suppose f of x is reducible, then you have this. Because tau star is a mapping. There we used tau star to be 1 to 1, here tau star is a mapping. So in the domain, two elements are equal means corresponding images in the codomain will be equal. So that is because tau star is a mapping. So you have this step, f dash of t equals this. But that would say that your f prime of t is not irreducible. That means it is reducible. That's a contradiction to statement P, which states that f prime t is irreducible. So you have the behavior of polynomials in fx and f prime of t to be the same. Just because we have established one-to-one onto homomorphism between fx and f prime of t. Now in the next video we will have the next lemma, namely lemma 5.3.4 as given in Hurston, and we will also have theorem 5.3.3 and a corollary to that theorem. So all this we will see in the next video. Thank you.